Hello everyone and welcome to our second real analysis lecture. Sorry it's been such a long time since the first one, but I think I got things set now where I can maintain a fairly consistent level of production as far as lectures go. Before we embark on new stuff, let me just remind all of you what we did in the first lecture. We proved two things. The limit as x approaches 0 of sine x equals 0. And the limit as x approaches 0 of cosine of x, we proved that that equaled 1. Now, before we do new stuff, some other reminders also. This is the definition for a function being continuous at a point, that point being f of x naught. Now think about this. Let's let x be x of naught plus delta x. So then the limit as x approaches x of naught of f of x is exactly the same as the limit as delta x approaches 0 of x of naught plus delta x. X of naught plus delta x they're exactly the same thing. And as delta x goes to 0, x of naught plus delta x goes to 0. Let's see, is that really true? No, I don't think so. As delta x goes to 0, x of naught plus delta x is going to go to x of naught. So as delta x goes to 0, x goes to x of naught. to compute the limit of f of x as x goes to x of naught is exactly the same thing as computing the limit of f of x of naught plus delta x as delta x goes to 0. And because of that, we have an alternate definition of continuous at a point. Here's the one that we started off with. This is the definition for continuous at a point. Now we can rephrase this in terms of delta x. And take a look at this. This is not right. Limit of f of x as x approaches x0. Nope, not x of naught, but f of x of naught. If this was causing you some grief, I apologize. Now we have two equivalent definitions of continuous at a point. Take a look at them, and then I'll state what's on our agenda for today. Take a look at them. Hit the pause button if you need to write them down in your notes. And please do take notes. Please do take notes when you're watching this. And scrutinize everything that I do so that you're not just watching passively. But I would like for you to be thinking along with me so that in case I do something like this, you'll stop and say, "What? No, that can't be right." Instead of just writing it down. But yeah, take notes. And of course, they're your notes, so you're welcome to embellish and augment the notes in any way that you see fit, any way that will add clarity to what I'm writing. Anything that, when you review the notes, will trigger a memory and make you go, aha, okay, I understand why this is true. So yes, watch studiously, take notes, think as I'm thinking, and try to second guess me when I'm thinking too. That's a good thing. When I write something down, be thinking, okay, now wait a minute, where's he going with this? Don't necessarily wait for me to tell you where I'm going. It's a good thing to be thinking ahead, even if your intuition misleads you, because if you're thinking ahead, then you have to understand what it is I'm doing now in order to think ahead, and that's good. So we have these two equivalent definitions of continuous at a point. Here's our immediate agenda. Those are our two immediate agenda items. Prove that sine of x is continuous at every real number x of naught. Prove that cosine of x is continuous for every real number x of naught. And before we go ahead and prove the first, we want to remember two things from trigonometry of all courses. The formula for the sine of the sum of two angles, we want to remember that. And the sine of the sum of two angles is sine of the first cosine of the second, plus, and this sign is the same, plus here, plus sine of the second times cosine of the first. The other thing that we need is input the formula for the cosine of the sum of two angles. And it's going to be cosine of the first times cosine of the second minus whatever these two signs here are, whatever this sign is here, this sign is the opposite. So cosine of the first, cosine of the second, minus sine of the first times sine of the second. And this should jive with what we know from other trig identities. For example, suppose this is the sine of, suppose this is the cosine of a plus a. Then this is really the cosine of 2a. Now, we plug in a for b and we get cosine of a, cosine of a. Ooh, that's cosine of a squared. Sine of a times sine of a, that's sine of a squared. Cosine of 2a equals cosine squared a minus sine squared a. That's another identity that we know. So apparently we got this one right. Let's do the same thing with this one. Suppose we have sine of a plus sine of a. Then this is really sine of 2a. In every place we see a b over here, we put an a. So what do we get? Sine of a cosine of a plus sine of a cosine of a. That's 2 sine of a cosine of a. But sine of 2a is 2 sine of a cosine of a. So, yep, we remembered these two identities correctly. And we're going to use these two identities to show that sine of x and cosine of x are continuous at all values of x of naught in the real numbers. Yeah, to prove that sine of x is continuous at any value of x, x naught, in the real numbers, all we have to do is show that the limit as delta x goes to 0 of sine of x naught plus delta x is equal to sine of x naught. So let's do it. This is the sine of the sum of two angles. So we get to use one of those identities right away. So what was it? Sine of the first times cosine of the second plus, with the sum of two angles, the sine of the sum of two angles. This sign stays the same. If it's plus here, it's plus here. So sine of the first, cosine of the second, plus sine of the second times cosine of the first. Cool. And now I look at this and I say I have the limit of the sum of two functions. I can break that up into the sum of the limits. So I'll have the limit of the first, sine of x naught cosine of delta x, plus the limit of sine of delta x times cosine of x naught. Ah, looking good. Now, in each case, here and here, I have the limit of a product. And remember, the limit of a product is the product of the two limits. So essentially, I can say limit is delta x goes to 0 of sine of x naught times limit is delta x goes to 0 of cosine of delta x. Oh, this is looking real good. Plus whatever this turns out to be. And this is the limit of a product also. So we have the limit of the first function, sine of delta x, times the limit of the second function, cosine of x naught, And just stop and reflect on that for a second. X of naught is a constant. So if I take a constant and plug it into the sine function, I get another constant. So sine evaluated at x naught is a constant. So this is the limit of a constant, and that's just going to equal the constant itself. Sine of x naught. Now this second thing, this was one of the two limits that we developed in the last lecture. The limit is delta x goes to 0 of cosine of delta x is 1. And this guy, this is the other limit that we developed in the previous lecture. The limit is delta x goes to 0 of sine of x. That's 1 also. And then 1 also, my foot. I hope your heart stopped temporarily when I said that. Limit is delta x goes to 0 of sine of x. What is that? Forgive me, I'm on autopilot, but I hope you're not on autopilot. The limit of sine of delta x as delta x goes to 0 is 0. And then this thing, x naught is a constant, so cosine of x naught is a constant. And the limit of a constant is the constant itself, cosine of x naught. So what do we get? We get sine of x naught times 1 plus 0 times cosine of x naught. And all of that equals sine of x naught. So let's summarize what it is that we just showed. We started out with the limit as delta x goes to 0 of sine of x naught plus delta x. And we wound up with sine of x naught. There, we nailed it. Take a minute or two to look at that, copy it down, hit the pause button if you need to, and then we'll go on to the counterpart of this. We're going to show that cosine of x is continuous at each value of x. going to show that the cosine of x is continuous at each point x of naught for every real value of x of naught. Based on the observations that we made at the beginning of class, that's what we got to show. And this is what we're going to show. Okay? Before I take this next step, I'm going to ask you, what do you think I should do in this next step? What do you think our next step should be? Think about it for a second. Give it some thought. Do you have an answer? If you said use the trig formula for the cosine of the sum of two angles, you're right. So what we're going to get is the limit as delta x goes to 0 of, and let's see, how did that formula go? Cosine of the first times cosine of the second. And if this is a plus sign here, then with the cosine formula for the sum of two angles, we have a minus sign here. Whatever is here, we have the opposite sign here. Cosine of the first, cosine of the second, minus sine of the first, sine of the second. Okay, take some time, write that down. Now what should we do? We have the limit of the difference of two functions. And we know that the limit of a sum or difference is equal to the sum or difference of the limits. So this will become the limit of the first term minus the limit of the second term. Now what should we do next? Here we have the limit of a product, and we know that the limit of a product is the product of the two limits. So we can apply that fact here and here. So this will become limit as delta x goes to 0 of cosine of x naught So that's the limit of the first, times the limit of the second. Limit as delta x goes to 0 of cosine of delta x. So the limit of a product is the product of the two limits. And now we're going to move to this term and do exactly the same thing. Limit of the first, sine of x naught, times limit of the second, sine of delta x. Now, what do we have here? X of naught is a constant. It's a fixed x value. So if we plug a constant into the cosine function, we get another constant. So this thing is just the limit of a constant, and that turns out to be the constant itself. Now this term, this is one of those limits that we derived last time and that we made note of at the beginning of this lecture. As delta x goes to 0, cosine of delta x goes to 1. And remember, as delta x goes to 0, sine of delta x goes to 0 also. That's the other limit that we made note of at the beginning of the lecture. So all we have left is this factor right here. And again, x of naught is a constant. If we plug this constant into a function, we get another constant. So this factor is just the limit of a constant. And we're going to get the constant itself, sine of x naught. So we get cosine of x naught times 1 minus sine of x naught times 0 and that's going to give us cosine of x naught. Now let's recap what we just did. We started out with the limit as delta x goes to 0 of cosine of x of naught plus delta x. And what did we end up with? We ended up with cosine of x of naught. And that's exactly what we had to show that the cosine of x is continuous at every real number x of naught. There, we did it. Got to be careful here. Can I plug 0 into the natural log function? Mm-mm. Can I plug a negative number into the natural log function? Nope. So the natural log is continuous, but not for the entire set of real numbers. The natural log of x is continuous for the entire set of positive real numbers. The quotient of continuous functions is continuous at each point x of naught, except those values of x of naught that cause division by 0. And the product of continuous functions is continuous at each real number x of naught. These will accept without proof. So e to the x is continuous, natural log of x is continuous on the set of real numbers. Natural log of x is continuous on the set of positive real numbers. The product of continuous functions is continuous for all real numbers. The quotient of continuous functions is continuous at each value x that doesn't cause division by 0. Yeah, we have an alternative definition for the derivative at x of naught. And think about this. If we look at this definition, then up here, this is x of naught plus delta x. And let me be more specific. If we compare this definition with this definition, then we'll see that x down here is exactly the same as x of naught plus delta x up here. So this is f of x naught plus delta x. And down here, this is x of naught plus delta x minus x of naught. That's just delta x. So the two definitions are equivalent. We'll use one or the other depending on which is more expedient and which is more advantageous. So if f prime of x of naught exists, then we say that f of x naught is differentiable at x naught. And if the derivative at x of naught exists for all real numbers x of naught, then we say that f of x is differentiable, period. So if f prime of x naught exists for all real numbers x of naught, then we just say f of x is differentiable. Classic theorem from real analysis. If a function is differentiable, then it's continuous. So if we can compute the derivative of a function for a particular value of x, then we know automatically that it's continuous at that same value of x. And looking at this restatement of our proposition, here's our hypothesis. So I have no idea how to prove this. So because I don't know what to do, I'm just going to start by assuming that my hypothesis is true, which I have every right to do. I still don't know what to do. So I'm actually going to write out the immediate consequence of my hypothesis. If f prime of x naught exists, then I can write this. F prime of x of naught is equal to the limit as delta x goes to 0 of f of x naught plus delta x minus f of x of naught all over delta x. This is true because f of x is differentiable at x of naught. I've stated my hypothesis and I've written down an immediate consequence of my hypothesis. I still don't know what to do. So I'll look at what it is I'm trying to prove. I'm trying to prove that f of x is continuous at x naught. Well, what does that mean? What do I have to show that f of x is continuous at x naught? Since I don't know what else to do, I'll write down what I have to show to prove this. And what is it that I have to show that f of x naught is to show that f of x is continuous at x naught? There are two ways that I can write this. I'm going to write it this way. The limit as delta x goes to 0 of f of x naught plus delta x is equal to f of x naught. This is what I'm going to have to show. Okay, here we go. I sure hope we can do this. I'm starting out with this thing. And what do I know about this thing? F of x of naught plus delta x is part of something that I'm assuming to be true. I'm assuming that the limit of this piece of junk right here is equal to f prime of x of naught. So I'm going to take this thing and try to turn it into this thing because I know what this thing is equal to. Now, will that help in the long run? That beats the heck out of me. But I'm going to take this thing and I'm going to subtract f of x of naught from it. So let's say limit as delta x goes to 0 of f of x naught plus delta x. Okay, and over here I'm going to subtract f of x of naught. Well, I can't just whimsically do that. I changed the value of this expression by subtracting f of x naught from it. To atone for my sin, I'm going to have to add it back. And I'm going to add it back here. Why, I don't know, but I sure hope it works. But see, I haven't changed anything. I took this expression, and then I added f of x, and then whoops. Hold on. There, that's much better. F of x naught here. So I started out with this expression, and then I added f of x of naught, and then I subtracted f of x of naught. So I haven't changed anything. Now, what I really have is the limit of this thing minus f of x naught. What I'm going to do is make use of some observations that we made a minute ago. This is a constant, isn't it? I take the constant x of naught and plug it into the function f. So this is a constant. What would happen if I computed the limit of this constant? It's just the same as the constant itself, right? So I can say, okay, minus limit as delta x goes to 0 of f of x naught. I haven't changed anything. This thing is the same as that thing. But now I'm starting to see where I might be able to do something. Sure hope this works. But I do have an idea, and I think it might work. And if it doesn't, well, guess what? I'll just destroy this video and you'll never know. You'll never know I goofed up. Okay. Now, continuing on, f of x naught plus limit as delta x goes to 0 of, now think about it. I have the limit of this thing minus the limit of that thing. I have the difference of two limits. Isn't that exactly the same thing as the limit of the difference? See, limit of f of x plus or minus g of x is equal to limit of f of x plus or minus limit of g of x. Did that make it on? Oh, shoot, it didn't. Okay, I'll just rewrite it. Limit of f of x plus or minus g of x equals limit of f of x plus or minus limit of g of x. Now, was that any better? Okay, that was a little better. Well, you know what? This is an equation. And we don't really think along these lines too often, but equations are two-way streets. Usually, though, we read things from right to left. But an equation is a two-way street, which means we can also read it from right. We usually read it from left to right, but we can also read it from right to left. In other words, the limit of one function plus or minus the limit of another is just the limit of the sum or difference of those functions. Well, I have the limit of one function minus the limit of another. I can rewrite that as the limit of the first. Come on, Pat. Yeah, that's right. There. I just rewrote the limit of this function minus the limit of that function as the limit of the difference of the same two functions. And I can do that. Now, I think I'm getting closer to something that has meaning. And I sure hope this works. Yeah. I want delta x to be underneath this because then this will look like the derivative. So I'm going to take f of x naught plus delta x minus f of x naught and divide it by delta x. Well, I can't just arbitrarily and whimsically divide this thing by something. So I have to atone for that by multiplying by that same thing. So let's see, delta x over delta x, that's just 1. Okay, so big deal. I took this expression and just multiplied it by 1. I haven't changed anything. Now, what I really wanted was this, because this is the derivative of f of x evaluated at x of naught, and I know what that equals to. I know that exists. But I got this delta x here. What do I do? Well, I'm computing the limit of this whole thing times that thing. It's the limit of a product. I can rewrite that as the product of the two limits, like this. F of x naught minus, no. F of x naught plus delta x minus f of x naught all over delta x times limit as delta x goes to 0 of delta x. And I know what each of those things is. This thing is f prime of x of naught. This thing is 0. We are at the brink of entering the promised land. Here it is. Here it is. We have f of x naught plus f prime of x naught times 0. Well, that's just f of x naught. That's what we wanted to prove, son of a gun. Wow, that fits, doesn't it? Okay. We proved it. Look it over, finish writing this down, and before we say, okay, we've proved it, we did it, yay, we can celebrate. I just want to highlight how part of the hypothesis figures into this proof. So finish tying up loose ends and looking this over and writing this down in your notes. And then I'm going to address a subtle point. Because it's possible to look at each step of this proof and understand each step and still not realize the full significance of the hypothesis. This is kind of subtle, but we should take a look. F prime of x naught is a real number. In particular, this limit is a real number. And I'm going to have to write this down lower. See, we showed that the limit as delta x goes to 0 of f of x naught plus delta x is equal to f of x naught plus the limit of this piece of junk, which turns out to be f prime of x of naught, times delta x, which goes to 0. Now, since f prime of x, this thing, is just a real number, then this limit is of the form 0. This limit is of the form f prime of x of naught, which is a constant, times delta x. We get a constant, we get the limit. F prime of x of naught times 0. And this is just a constant times 0, which is 0. This all magically disappears and we're left with f of x naught. But what might have happened if f prime of x naught didn't exist? In other words, suppose f prime of x was not a real number. Maybe f prime of x naught is infinity. Ha ha ha. Okay, let's go back to where we were before. The limit as delta x goes to 0 of f of x naught plus delta x equals f of x naught plus the limit of this pile of junk, which before turned out to be 0, very conveniently. And it left us with f of x naught. So with this pile of junk being 0, we had limit as delta x goes to 0 of f of x naught plus delta x equals f of x naught. And we go, yay! It's continuous at x naught. But now suppose the derivative doesn't exist. Maybe this limit turns out to be infinity, for example. And this is of the form infinity times 0. And from calculus, we know that this is not necessarily 0. This could be infinity. This whole limit could be infinity, or it could be any other real number other than 0. Yeah, what do we call this thing? An indeterminate form. Because based on the fact that it has the appearance of infinity times 0, we can't tell what this limit is going to be. And it could be infinity, or it could be equal to any real number other than 0. And if that's the case, this limit does not equal f of x naught, and we don't have continuity. So here's how the fact that the derivative existed proved to be important in our proof. Since the derivative existed, this expression right here had to be a real number, not infinity. And a real number times something going to 0 goes to 0. So our hypothesis that the derivative exists played a subtle role in this proof. And I just beat that to death because I wanted you to see how that turned out to be an important hypothesis. Well, I think that will conclude this lecture. Study it carefully. I promise it will only be a couple of days before I have lecture 3 online. So study this and enjoy it, and I do mean that. I've told my other classes this, I'll tell you this also. In Ecclesiastes it says there's nothing better than for a man or a woman to see good for all their hard work. The bottom line is, if we work hard, we'll enjoy the fruits of our labors. So study this, work hard. I'll have another video coming soon. And in addition to working hard, please play safe. Exercise soundness of mind in everything that you do. And I am eagerly looking forward to the day when I see your bright, sunshiny faces right in front of me in this classroom. So please exercise soundness of mind, and please stay healthy.